Europe is a cozy place, not too warm in the summer, not too cold in the winter, not too wet and not too dry. But the climate in Europe depends strongly on the Gulf Stream, and for us over here, that the Gulf Stream stops or weakens is one of the scariest possible consequences of climate change. In case you're in the US and don't really care, let me mention that the US is the biggest importer of European wine, so you should care. But can the Gulf Stream really stop as the headlines scream? No, it can't. Why? And what might happen instead? That's what we'll talk about today. A big thank you to all our sponsors on Patreon, especially those of you in Tier 4 and higher. This channel would not be possible without your help. London is further north than Boston, and yet the climate in London is considerably milder than in Boston. London doesn't get as cold in the winter and not as warm in the summer as Boston does. This makes you think there's something extraordinarily precious about Europe. But actually, it's just physics. Yes, physics. Because you see, the Earth is round. And not only this, it also rotates. And the surface drags the air with it. That might make you think there shouldn't be any wind on the ground, but the other thing that's going on is that the sun heats up the air. And it heats it up more in the regions that get more sunlight, which are those close to the equator. The hot air rises and must come down somewhere. This creates loops in the south-north direction. They're basically convection cells. Now, if you look at one particular location on the surface of Earth, then the speed from the rotation is larger at the equator, because there's a larger distance to cover when you go round around. This means if the rotation drags air with it, then the velocity in west-east direction is faster at the equator. Still with me? Then you add on top the circulation that comes from heating by the sun. As a result, you get some of that air from the equator redirected towards the poles. But there, the surface of Earth is slower, so the air is now faster than the surface of the Earth. And some of that air from the middle regions is transported to the equator, where it's now slower than the rotation of Earth. That's why at the equator the wind tends to blow east to west, so against the rotation of the Earth, and between the equator and the poles the wind tends to blow west to east in the same direction as the Earth turns. These winds are also called the Westerlies and Easterlies. In case that was too comprehensible, you could instead say that angular momentum is conserved, or that the Coriolis force acts on the air, or you could hit yourself over the head with this 600-page book. The physics will remain the same. The Earth is a sphere, and it rotates, and that's why the wind over Europe normally comes from the west. Indeed, let's look at what it does right now. This is a visualization of global weather data from a website called earth.nullschool.net. Shows you everything from temperatures to wind to water currents. What you see here is the wind speed, and you can see how it's patiently blowing west to east in both hemispheres. That the wind between the equator and the poles tends to go west to east and not the other way around is the major reason why the climate in Boston is so different from London. It's because water acts as a temperature equalizer. It stores heat much better than land does. In the winter, land masses cool out faster, and in the summer they heat up faster than water. If the wind that blows towards a region typically comes over large chunks of land, as it's the case in Boston, you'll see more temperature variation than when it comes over water, as it's the case in London. Indeed, if you look at Vancouver in comparison, then the weather there is much milder than Boston and much more comparable to London. Okay, so now what's with the Gulf Stream? The Gulf Stream is a warm ocean current. It originates in the Gulf of Mexico, from which it got its name. Then it flows north along the east coast of the United States and Canada. The Gulf Stream was discovered 500 years ago by a Spanish explorer, Juan Ponce de Leon, who noticed that it was near impossible to travel down the coast of Florida. You can see the Gulf Stream doing its thing on the same website I mentioned previously. The color now shows water surface temperature, and the arrows show the water currents. This is the east coast of Florida. You can clearly see how the Gulf Stream goes north and then turns east, branching out into a turbulent tail. This ocean current then continues across the Atlantic Ocean towards Europe. All in all, the current makes one big circle that's called the North Atlantic Gyre. Strictly speaking, the part of that gyre that goes from the American East Coast to Europe is not the Gulf Stream anymore, but it's still often called Gulf Stream out of simplicity. The major reason for the Gulf Stream is again that the Earth turns, plus that the wind drags on the water. The reason the Gulf Stream is so important for the weather in Europe is that it warms the water in the north, and that warms the air above the ocean. And since the wind over the ocean usually blows from west to east, that brings warm air to northern Europe. The Gulf Stream doesn't only bring warm water to Europe, a lot of sea animals use it for transport as well. This whole gyre business and so on isn't specific to the North Atlantic. The same thing is going on in any other large body of water that's surrounded by enough land. There is, for example, also a current in the Pacific Ocean that's similar to the Gulf Stream in the Atlantic Ocean. It's called the Kuroshio current. Let's have a look at what this current is doing right now. Where is Japan? Here we go. Like the Gulf Stream, the Kuroshio current is a warm, fast-flowing ocean current that originates in the tropics and flows towards the poles, making its way up the east coast of a landmass, in this case Japan. It's part of a circulation called the North Pacific Gyre. The Gulf Stream should not be confused with the jet streams. The Gulf Stream is an ocean current. The jet streams are air currents. And yes, that's a plural. I know we normally talk about the jet stream, but there is also a jet stream in the southern hemisphere. It's somewhat unimaginatively known as the southern hemisphere jet stream. It too blows from west to east because, remember, the reason for the direction of the wind is just the rotation of the Earth, and the southern hemisphere of the Earth, believe it or not, rotates in the same direction as the northern hemisphere. The jet streams come from instabilities in pressure and temperature gradients high up in the atmosphere. They blow more or less persistently at altitudes between 6 and 10 kilometers with the speed of typically 160 up to 400 kilometers per hour. That's a lot, and it's the reason why flights from the US to Europe are sometimes up to an hour shorter than those from Europe to the US. It's because when going west, pilots will try to stay above or below the jet stream, while going east, they have it in their back and fly in it. Here you can see how the jet streams are doing their blowing. The color now shows the wind speed at high altitude, not the temperature, and the pink-white part is the fastest. The jet streams were only discovered in the 1930s, when scientists started sending weather balloons high up and the balloons kept drifting off. But there is a big difference between the northern and southern hemisphere, which is that there is more landmass in the north. As we saw earlier, land doesn't store heat as well as the ocean, so there are bigger temperature changes in the northern hemisphere. There are also more mountain ranges that just get in the way of the jet stream. This is why the jet stream in the northern hemisphere is typically more wavy and meandering than the jet stream in the southern hemisphere. So, jet streams are high-altitude winds that go that way, and the Gulf Stream is an ocean current which goes that way. The major driver for both is sunlight and the rotation of the Earth. Okay, so now what's with the supposed collapse of the Gulf Stream? Those headlines are based on a confusion between two different ocean currents, the Gulf Stream and the Atlantic Meridional Overturning Circulation, AMOC for short. It's also known as the Atlantic Thermohaline Circulation, different word, same thing, but not the same as the Gulf Stream. The AMOC is really a remarkably complex and super confusing network of circulations, and not just one, but it has one major feature. It transports warm water from near the equator towards the North Pole. On the way to the North Pole, the water cools and sinks down, goes back south, and the cycle repeats. The important point is now that the AMOC combines with the Gulf Stream, so that, in effect, the Gulf Stream is directed further north. The same thing does not happen in the Pacific Ocean. There's also an overturning circulation in the Pacific Ocean, but it doesn't cross the equator and it doesn't go as far up north, so it has far less impact on the climate. What climate scientists worry about is now that an increase in global temperature could impede this overturning circulation in the Atlantic Ocean. That's because the ice at the poles isn't salty. If it melts, that decreases the salt content of the water. If the water is less salty, it has a lower density, which makes it harder for the water to sink down. This could interrupt the overturning circulation. When the overturning circulation stops, then the Gulf Stream will no longer get this extra push to the north. This would mean that Europe will cool down. Simulations with climate models have shown that the average temperatures in Europe could go down by as much as 5 degrees. This figure shows the change in air temperature that we might see in Europe. So that's the thing that everyone is worried about, that the AMOC will stop. However, this would not mean that the Gulf Stream will stop. The Gulf Stream is caused by the rotation of the Earth. The only way to stop the Gulf Stream is quite literally to stop the Earth from turning. Even driving a pickup truck isn't going to make that happen. And if the rotation of the Earth really was to stop, trust me, you'd have better things to worry about than the Gulf Stream. It's not only newspapers which constantly conflate the Gulf Stream with the AMOC. The same thing happens, unfortunately, in a video from Kurzgesagt about the Gulf Stream. It's to date been watched by more than 5 million people. I'm afraid this makes it near impossible for me to weed out this confusion, but at least now you can't blame me for not even trying. If the AMOC would turn off, what'd happen in the long run? It probably wouldn't just turn back on again, even if temperatures go back down. It might take thousands of years for the circulation to return, if not longer. That the AMOC stops is one of the possible climate tipping points that'll not reverse even if we're all nice kids. However, the idea that the AMOC is a tipping point is based on an extremely simplified model that doesn't take into account the full complexity of the real ocean currents. Unfortunately, the current models just aren't good enough to make reliable predictions. For the same reason, it's difficult to say how high the risk is that the AMOC will stop and at what amount of warming. It's a super controversial topic among climate scientists. Some have claimed that there are signs that the AMOC is slowing down. Then again, others have said that the data aren't convincing and we might just be seeing natural variations. But maybe we don't want to make a big global experiment to find out. Unpopular opinion that comes from my friend the singing climate scientist Tim Palmer: when the AMOC stops, that might not be such a bad thing, because that'll reduce the flow of warm air to the poles, slow down the melting of ice up there, and that might prevent much of sea level rise. And you guys in the US can then import our ice wine. Many thanks to Fabian Roquet and Tim Palmer for helping with this video. Any remaining blunders are exclusively mine. So it turns out that the major reason for the weather on our planet is that the Earth rotates. But how do you do physics in a rotating system? A great way to find out is with Brilliant's course on classical mechanics. It has a really good introduction to the Coriolis force, which is another way to understand why the westerlies blow westerly. Or maybe you're more interested in quantum mechanics. In this case, let me mention I work together with Brilliant on a course that accompanies my videos on quantum mechanics. This course will introduce you to quantum mechanics starting from the very basics, so you don't need to be an expert already to understand it. It's an introduction to interference, superpositions and entanglement, the uncertainty principle and Bell's theorem. And like all their courses, it comes with interactive graphics and follow-up questions. Brilliant has courses on a large variety of other topics in science and mathematics. It's a fresh and new method of learning that I've found to work for me extremely well. Their courses all come with interactive visualizations, and that really lets you get a feeling for how things fit together. If you're interested in trying Brilliant out, use our link brilliant.org/Sabine and sign up for free. You'll get to try out everything Brilliant has to offer for a whole week, and the first 200 subscribers using this link will get 20% off the annual premium subscription. Thanks for watching. See you next week.